Hey everyone, today we'll be going over LeetCode problem 141, linked list cycle. This is another problem of the Blind 75 list, which is a list of problems commonly asked during technical interviews. In this problem, we are given the head of a linked list, and what we want to do is determine if the linked list has a cycle. And we are told that there is a cycle in a linked list if there is some node in the list that can be reached again if we continuously follow the next pointer. So what we need to do is return true if there is a cycle, otherwise return false. Now I have here an example drawn for us. There is one linked list with a cycle in it, and a second one with no cycle. We can see that if we follow along the first linked list, which has a 3 as its head, we follow each pointer one by one, and we would get to a point where we revisit the same nodes. We see that we go from the 3 to the 2 to the 0 to the -4, and the -4 then points again to the 2. So we would then visit this 2 again, and we know that there is a cycle because we see a node which we already visited. In the second case of the second list, we see that we go from the 3, which is the head, to the 2, to the 0, to the -4, but this -4 points to a null as its next pointer. Therefore, the linked list comes to an end, and there is no cycle because we have not revisited any of the same nodes. Now, what we want to do is determine whether or not these linked lists have a cycle and determine an algorithm which can do this efficiently. The algorithm we will use is Floyd's tortoise and hare algorithm, which will allow us to solve this problem in a linear time complexity and a constant space complexity. Now we know, of course, that we could go along the linked list and each time add the node to a hash set. And then when visiting a new node, we'd check to see if that node is in the hash set. And if so, we'd know that we'd already visited that node, and so we'd return true, that there is a cycle. However, that would take linear space complexity because of the use of the hash set. Floyd's tortoise and hare algorithm allows us to solve this problem using simply 2 pointers, so it is constant in space complexity. Now what we're going to do is simply have 2 pointers, a fast and a slow pointer, and we're going to initialize these both to the head. We're going to go through this linked list, and during each iteration, we're going to move the fast pointer twice, while the slow pointer only once. Let's run through this linked list as an example. Both of these pointers start at the head, but for the first iteration, the slow pointer will then move to the 2, while the fast pointer will go to the 2, and then to the 0. We're going to have another iteration. The slow pointer is going to move to the 0, and the fast pointer is going to go to the -4, and then to the 2 once again, because the -4 has the 2 as its next. We're going to have a third iteration, and then the slow pointer will move to the -4, and the fast pointer will move to the 0 and to the -4. Now, because at this point, we see that the fast and the slow pointer have reached the same node, meaning that we see that the fast pointer has caught up once again to the slow pointer. This means that the linked list we are currently analyzing has a cycle, and so we must return true. This algorithm that we are using would run until we ever reach a null point. So for example, in this second linked list, we see that there is no cycle, but let's run through this algorithm to show how we would return false. Once again, we would have both our fast and our slow pointers initialized at the head, which is a 3. During the first iteration, we would move the slow pointer to the 2, while the fast pointer would go to the 2 and then to the 0. During our second iteration, our slow pointer would move to the 0, while our fast pointer would move to the -4 and to null. Now at this point, we see that our fast pointer has reached null. Therefore, we would end our algorithm. And because during this algorithm, we have never reached a point where the fast pointer has caught up once again with the slow pointer, we would return false in this case. So basically, we'd have these 2 pointers, a slow and a fast pointer. The fast pointer will move twice during each iteration, while the slow pointer once. And during each iteration, we check to see if the fast pointer has caught up with the slow pointer. If it has, that means that we have a cycle in our linked list and we'd return true. However, if we go on until the fast pointer reaches a null point and we have never returned true, this means that there is no cycle. The fast pointer has never caught up to the slow pointer, and so at the end we could return false. Now, why is it that this algorithm has a linear time complexity? Well, we know that during each iteration, the fast pointer is moving twice while the slow pointer is moving once. So say we have this cycle with 14 nodes, and we're going to take the fast pointer to have a random position along the list compared to the slow pointer. Say that the fast pointer is 14 nodes behind the slow pointer, and there is one pointer between the slow and the fast pointer. And I just have a typo here. Since we have 1 plus 14 nodes, we're going to have 15 nodes total as our n. And so what we know, since the fast pointer is moving twice during each iteration, while the slow pointer is moving only once, we know that during each iteration, the distance between the fast and the slow pointer will decrease by 1 each time. So it'll go to 13, and then to 12, and so on. And so we know that we can have as many iterations as the number of nodes in our linked list max. And furthermore, if there is no cycle, during these 15 iterations, we will reach a point where the fast pointer reaches null. So we will never go over the linear time complexity. We can start off our code by checking to see if we have a null linked list. So if the head does not exist from the get-go, we know that we have a null linked list, and so we can return false, because if there is no linked list, there is no cycle. Otherwise, we want to initialize our fast pointer to the head and the slow pointer to the head. And while the fast pointer exists and it has a next, meaning that it never reaches null, and we need both fast and fast.next to be checked because we know that we're moving the fast pointer twice during each iteration, what we're going to do each time is make fast move 2 positions. So fast is going to be equal to fast.next, while slow is going to move 1 position. Then we're going to check to make sure if slow is equal to fast, meaning that fast has caught up to the slow pointer. And if this is the case, we want to return true because we know that we have reached the cycle. And if we're done with all this while loop and we never return true, we know that the fast pointer has reached null, and so there is no cycle, and we can return false. Notice that we're only checking for fast and not slow, because we know that the fast pointer is moving twice, and so if there is a pointer which will reach null, it will be the fast pointer to do so first. Let's make sure this runs. And we see that it works efficiently. Thank you so much for watching this video. If you enjoyed it, please subscribe to my channel. I'll see you on the next one.